Good morning and welcome to the second lecture of Pascal Auscher on the representation of solutions to the Resolvent problem.
Thanks, Albert. Okay, so let me start where I finished, maybe 2 or 3 lines before. So I was in the middle of explaining to you what we do with a bisectorial operator. With type omega on a Hilbert space, separable Hilbert space. Okay, and so we've seen a number of properties, and remember there was this class of functions. So mu is always going to be an angle which is sandwiched between omega and pi on 2. Even if I don't mention it, that's what I mean. And the sector S mu, maybe I should recall here, it was this double, in fact, double sector in a complex plane with angle mu here. It's the open double sector, okay, here and there. Okay, and then there was this, of course, this Cauchy formula to compute, to give a meaning to the operator. Okay, and nu was another angle sandwiched between omega and mu. Okay, and this defines an operator in L of H. Okay, this integral converges. It's independent of nu. Okay, and then T has H infinity calculus. Well, with angle omega prime, which could be the same or different depending on situation. Here it's going to be the same. If for all mu bigger than omega prime, we have at this operator psi of t with such psi, of course, is bounded in L of H, but with a bound that's controlled by the subnorm of psi on this open sector. Okay. Okay. Let me mention that this is stable. This is stable property under taking adjoint. Okay, so if T has an H infinity calculus, so does T star. But now, what do we do with this? So the object is, the purpose is to create operators that are a little more complicated than those with bounded holomorphic functions. So I need to explain what's a bounded H infinity S mu 0 calculus. Okay, what is this? Well, it is a map, in fact, that goes from this class, which I defined yesterday, into L of H. And so just to give a name to this map at the beginning, we call it phi t nu, with a number of properties that you expect from a functional calculus. So it's an algebra homomorphism. Okay, so for the product, okay, so it's a linear map, of course, and it respects the product. It should be bounded. So from this Banach space equipped with the subnorm into this Banach space equipped with the operator norm. Maybe F L of H. This way, it's okay. Then you should have some compatibility condition. That is, you expect phi t mu of the function identically 1 to be the identity, and phi t mu of what should be the resolvent function should be the resolvent of t. So where L lambda of z is just what you expect, lambda minus z inverse. Okay, and this should hold for any lambda that's not in S mu bar, I guess. All right, and the fourth property is a convergence property, which says that if you have Fn and F, which are a function in your bounded holomorphic function on S mu defined at 0, you assume that the sequence Fn is uniformly bounded. And you assume that Fn of z converges to F of z. Actually, for all z, it's enough. S mu union 0. You can impose, well, it's enough. Then this implies that the image of this phi t mu of Fn converges to phi t mu of F strongly. Okay, so for the strong operator topology. Okay, so this way you can make sense of various objects. And of course, I gave two sort of closed notion, H infinity calculus and this H infinity S mu 0 calculus. And of course, there is a theorem which says that if T has an H infinity calculus, then the map phi T mu exists. Okay, exists with these properties. Okay, and how is it defined? How is it defined? So for F, which is a bounded holomorphic function and S mu when defined 0, how do you define? You pick phi n, which is in this class psi S mu. Or I should mention that mu then is going to be bigger than omega here. Well, and then you pick any, you pick a sequence such that you impose psi n of z to converge with to f of z uniformly on compact of S mu, compactor of S mu. And then you define phi t mu of F. And if you pick H, a vector in H, the action on H is just going to be f of 0, which is a scalar number, times the projection on the null space of T applied to H. Do I define? Yes? So I prove that if I have this estimate, okay, I have the existence of this map. In the end, it's the same notion. I just wanted to make it different at first, but okay. Okay, so this is the way I define this map if I have this estimate. Okay, and then you take the limit when n goes to infinity of psi n of t. This psi n of t is defined by this formula above. Applied to not to H but to projection of H onto the closure of the range. Okay, so remember that for bisectorial operators, we always have the splitting of the Hilbert space into a null space and closure of the range. Okay, so these are the projections associated to this splitting. Okay, and of course this limit exists, and so you prove the limit exists, and then of course the limit doesn't depend on the choice of the psi n. This defines this action here, and in the end you prove all the properties that are there. Okay, so it requires some work, but it's not completely difficult. Okay, so but of course you may have another definition of another H infinity of another map, but in fact this map is unique. Is unique with the properties I to 4. Okay, and in particular, if you pick two different angles, mu and mu prime, then these two maps agree on the smaller space, which would be this one. Okay? So this allows me to, so from now on, we set f of t to be phi t mu of f whenever f is in one of those classes. Okay? Okay, so, and of course, if f is in the union of different classes like this, these objects are the same, so it gives a meaning to this notion. All right, so just a word. Here is a definition of the functional calculus, and for example, you want to check that when you apply this functional calculus to the resolvent function, you get the resolvent. Okay, it takes a bit of an exercise to check that the two definitions do give the same thing, but they do. Okay, so you have to believe me that once you have understood the functional calculus with these three properties, you can forget about the definition and compute as if you were dealing with holomorphic function. Okay, but now the main examples, the one we are really interested in for the application to boundary value problems. You have functions chi plus of z. Let me define this is 1 if z is in the right open sector. So remember that this is S mu plus here and S mu minus there. Okay, and 0 otherwise. Then, of course, you can define a minus function here by changing the plus to minus there. Okay. You can define a 0 function, chi 0, to be just 1 if z is equal to 0 and 0 otherwise. Well, it looks stupid, but it's useful. And you can also define a Signum function, which is the difference of the plus and minus functions. Okay, and all these four functions belong to the class in which we are interested. Okay, so what does it give? The existence of this functional calculus. Again, it's an assumption here. It's an assumption that we have such an estimate, but it gives a number of properties. So the proposition, if you want, if T has an H infinity calculus, then, well, first of all, these four operators are bounded operators in H. Second of all, chi0 of t is just a projection operator on the null space of t. Chi plus and minus, there are projections. Okay, so we set h plus minus of t to be the range of these projections. Okay, and there are projections, and it seems they are bounded, and they sum up to the identity. On, well, not exactly the identity, they sum up to being the projection on the range. In other words, the range of T closure is the topological sum of two spaces, which I'm going to call the spectral spaces. Okay, and this spectral space is exactly what I was telling yesterday. Let me redo the picture of the spectrum here. So this splitting tells me that I'm allowed to separate the positive part of the spectrum, meaning the part with real part, positive real part, with and separate with the part with negative real part. Okay, so there's a topological splitting in this topology of the Hilbert space. So that's good. Now, of course, here I take the sum. So the sum is a projection. Notice that the signum is just a difference. So, of course, many of you know the Hilbert transform. So there's a similarity, strong similarity with the Hilbert transform here. And in fact, let me just mention, should be 4. As the Hilbert transform. In this context, of course. And if you really take the context for which you have the Cauchy-Riemann equation, at first this signum of t is the Hilbert transform, the classical one. Now, with this notion, you can create a new operator, which I'm going to call mod of t. Of course, mod is a bad notation, but this is customary, so I use it, which is a product of signum of t times t. So this defines an operator with same domain as t, because signum is a bounded operator. By the way, not only signum is a bounded operator, but if you restrict it to the range of t, closure, it's an involution. Signum times signum is equal to 1. Okay? So the domains are equal because of this. And then this operator is now sectorial with type omega, where omega was the type of t. Okay? But now sectorial means that the spectrum is contained in S omega plus, well, S omega bar, S omega plus bar. Okay? So there's no other part of the spectrum. And for those who like square roots, no, first of all, it's sectorial. And then you can characterize the spectral spaces as a set of elements in the Hilbert space for which mod of t applied to H is equal to plus or minus t applied to H. But is a mod of t on separately the plus or spectral minus spectral space acts as t up to a sign. Okay? So it looks like a bad operator, but on a restriction, it's not so bad. Okay? And so let me just make a remark for those who know square roots of sectorial operator. So if t is bisectorial of type omega, this implies that t squared is sectorial of type 2 omega. Well, at least, okay? And sectorial operators of type less than pi have square roots within the class of sectorial operator. And you divide the angle by factor 2, so you recover sectorial operator of type 2 omega. So in other words, this is always defined whether or not you have H infinity calculus. But on top of that, if you have H infinity calculus, then this operator mod T that is now defined by this formula is equal to the square root. Okay, so you could bypass the H infinity calculus and just work with square roots, but the H infinity calculus gives you one important information, which is this splitting. Okay, this is the important thing here. All right. Another remark before I move on. So let me take a function psi in my favorite class of good bounded holomorphic function with a following integral condition. So I integrate over the half lines, positive and negative half line. I suppose that each of these two integrals gives me 1. Then you can create this operator, okay, and this operator will be defined in a strong convergence, so it converges strongly to the identity on, well, to the identity, or in fact, not to the identity, but to the projection on the range. Okay, so in other words, that gives me that for any H in the range, I am able to represent H by a converging integral of this type. Okay? And of course, this is a Calderon reproducing formula in this context. But you notice that in the function of, well, in the functional calculus of T. But you notice that this formula is not valid for any element of the Hilbert space, but only for those in the range, closer of the range. Actually, if H is in a null space, psi is a function in that class, so it's 0 at 0, so it sends the null space to 0. So in other words, if H is a null element, this would give 0, and of course it does. This integral cannot converge to H. Okay, so you have to put this restriction, and actually that's one of the main difficulties here in applying this technology to the boundary value problem. You always have to work in a range, and you have to be careful about that. Okay. All right. So a little bit more, and then I will be done with the functional calculus in the abstract. Of course, there is a semigroup now, okay, which is e to the minus s mod t, or s positive, okay. This semigroup exists just by a theory of sectorial operators. We said that this operator is sectorial of type omega. Omega is less than pi on 2, so we have a semigroup. And the theory tells us that this is a bounded analytic semigroup on H. So analytic means that mod of t times e to the minus s mod of t is bounded okay, by some constant times s inverse. Bounded, well, this is uniformly bounded for all s positive. It converges strongly to the identity when s goes to 0. And in fact, analytic also means that there is an analytic extension in a sector S with argument less than some angle pi over 2 minus omega, I think. Right. Okay, so let me not go into that. But now, so how is it defined? Well, this is defined by taking the function f of z to be e to the minus s signum of z times z, which is a bounded holomorphic function in our classes. Okay? So now, all right, so we're going to use this semigroup strongly. So the last thing now. Okay. And maybe the main theorem here is, okay, so I put H infinity calculus as an assumption to get some information. So now it's the criterion for H infinity calculus, and the answer is yes. So the following equivalent, T has an H infinity calculus with some angle, Let me not be precise about this. In our context, it's not an issue. In more abstract context, it could be an issue, of course. So this is equivalent to there exists a psi in this class, non-degenerate. Non-degenerate means that its restriction to the two sectors is not identically 0, okay, to each of these two sectors. Such that we have a square function estimate but for all h in a range, closure of the range. And this is equivalent to, for all such psi, we have this. And of course, the equivalent constants depend implicitly on the psi, but this is true for any psi. Okay, so this is the main criterion, which takes us back to harmonic analysis. This kind of square function is really seen as orthogonality, an orthogonality lemma, some kind of Kotler-Stein lemma could apply, or some kind of, you have to find orthogonality within the functional calculus to be able to prove something like this. Okay, so let me just mention that here, why do we need non-degeneracy? We need non-degeneracy to have both directions in the equivalence, but you always have, is always true for, so if three holes, then this implies that this is always true for any psi, whether or not it's degenerate, and for any h in the Hilbert space. Again, if h is a null element, this is 0 identically, so this contribution to the integral is 0. Okay. All right, so this is useful sometimes to have this in mind. So now the main application for us. Let's come back to DB. I'm done with the abstract things. Okay, so application. Okay, so we have, so remember we had this operator, matrix of operator D. Okay, it was defined informally as a first order differential operator, but now I want to define it with a domain. So my Hilbert space is, let me just mention, L2 of Rn, and its functions valued in some Cn. Okay, n was this product of the number of equations in a system times dimension 1 plus n. Okay, so the domain is a set of H for which div of H, so H is, sorry, the parallel part is in the domain of the divergence, seen as an operator, an unbounded operator on L2, and the tangential part is in the domain of the gradient. Okay? So with this makes D a self-adjoint operator on H. Beware, it's none. It's not neither positive, neither negative. Okay? It's a self-adjoint operator with a spectrum actually equal to the real line. Okay? So now we had this B which was, let me remind, the formula, it's not really important here. It's just to connect to the PDE. Okay, and we know from this lemma that, so it's a multiplication operator, okay, which is bounded in H and which is accretive on the range. Okay, so we have the real part of B, maybe in our context H is bigger than some kappa times the norm of H squared. So this is the L2 norm now for all H in a range. Okay, so this is the only condition that we have, and this is the only condition that we need. Good. So with this, definition, you can define dB and also BD. Okay, so theorem. So you define dB with natural domain. Okay, it's a set of H in H such that B of H is in the domain of D. Sorry for my D's. I should use curls maybe here, not to be confused with this one. When you type in tech, you can make the difference, but on the board it's more difficult. And then you have this one, such that, well, this is the domain of D. So you have two operators. I give a domain, and of course, I assume that dB applied to H is D applied to B of H, and then for BD, this is just composite, okay? And then the main theorem here is that, so dB and BD are, well, bisectorial operators. On H with H infinity calculus. Okay. And the angle here is just the angle that you pick up from the conditions on the B. That is, you have this B is bounded by some bound here, and the real part is bounded by some kappa. And then you pick up an omega here as a sector. Okay. All right. So let me mention this. This is easy. Okay, but this is harder. In fact, this is sort of equivalent to the Kato solution of the Kato conjecture. And in this framework, this is really a theorem of Axelson, Keith, and McIntosh. They transpose the technology of the proof of the Kato conjecture into this framework and really prove that. Okay. So, so the proof of this is really a singular integral. It's not abstract, it's really concrete thing, uses Carlson measures and these kind of tools from harmonic analysis. Sorry? Yeah, so in other words, yeah, the proof goes by proving you take you take your favorite psi, for example, which is z times 1 plus z squared inverse, and you prove the square function for this psi. Okay. Yes, it's true in general, in the setup that I gave you. Okay, so what is the application for us, of course, in our context? Maybe I mentioned, I talked a lot about dB. dB came up in the Cauchy-Riemann equation, and we come back. BD does not show up, but in fact, if you take the adjoint of dB, it's B star D, and B star has the same property as B. I mean, these properties on B are stable under taking adjoints. So the application. Okay, so we pick, so again, we have H, which is L2. So we have this space H2D, which is just the range of D in our context. This is the same as the range of dB. Let me just mention, of course, these on the left. And again, this is, let me just mention, this is a set of H in L2, well, in L2, such that the curl of X with respect to X of the tangential part. So remember that these elements have scalar part and tangential part like this. So the tangential part should have curl 0. Okay, and from the theorem that we stated before, it's also equal to two spectral spaces, which I'm going to denote H2 plus dB plus H2 minus dB. Okay, so the 2 is, was not in notation before, but there will be a P soon, so I use the 2 now. So these are the spectral spaces associated to the bisectoral operator dB. Okay? So then now you can take an element in the positive spectral space, and you can set f of Tx to be E minus T mod dB applied to H at X. Okay, so for each T, this is an L2 function. So there's no problem in the definition. So T is here is positive. X is in Rn. Okay, and well, if you compute now d by dt of f, you can compute it in a strong sense if you want. You have this theorem group, it's analytic. It's mod dB minus mod dB E minus T, so mod dB of H. But H has a property that it's preserved by the action of the projection on to that spectral space. So I can replace H by chi plus dB on H. The chi plus dB will commute with the exponential, just the algebra property. And what is mod dB times chi plus? Well, this is a restriction of mod dB on the plus spectral space. And I told you that on this space, mod dB acts as dB. So in other words, it's equal to negative dB times f. So we have naturally constructed a solution to the Cauchy-Riemann system. The first equation was there. The second equation is because it's built in the spectral space. And of course, the L2 lock condition here, it's there. Okay? So in other words, f is not only a weak solution of this of CR, it's even a strong solution, okay, in the semigroup sense. So let me write this. plus, so F is a strong, well, solution to CR. Maybe I should, well, CR was, maybe I will write it again. So CR was d by dt f plus db f equals 0 in distribution sense. There was this curl condition also in distribution sense, and there was a requirement that f was in L2 lock. Okay. All right. So we have a way of constructing solution by this semigroup method. That's like when you do potential theory, you have a way of constructing solution by harmonic measure method. That's another way. Okay. In the end, everything will match. But for the moment, I don't know if I want to be coherent in the progression. Okay, in the end, I will tell you that, yes, you'll have the same solutions. Okay, but for the moment, I don't know. I construct a solution. Okay, it's a method. So this solution has, so this solution, of course, is given by a semigroup. So a number of properties that you have. Of course, you have the sup L2 estimate, which is actually equivalent to h in L2. You have a square function estimate, which comes from the H infinity calculus. Okay. And, well, usually what we are interested in harmonic analysis is there another one, which is a non-tangential maximal estimate. So what would it be? It would be something like n tilde star of E minus T mod dB of H. Is it an L2 function equivalent to H in L2? In fact, let me just make it, okay, this is true for all H in the range. You don't need specifically for H to be in the plus space. So the plus space is needed to get a solution to this equation, but you can work with a semigroup without thinking of this equation here. So what is n tilde? Well, you have to define Whitney regions in the upper half space, so which are going to be, well, something maybe. You pick an x, you take something like this, which I'm going to call a Whitney region. So here you have t, which is up here. Okay, so you have some interval, which is C0 t over C0 t, and C0 is some constant bigger than 1, and times the ball centered at x and radius comparable to t with some constant C1, which are adjustable to whatever you want to do. And then you take n tilde star of some function g at x to be the sup in t positive of the averages on this wtx of g sy squared with respect to Lebesgue measure 1/2. So this kind of maximal operator was non-tangential maximal operator is a variant, is an L2 variant of the pointwise one. This was introduced by Kenig-Pipher in the context, and you see it looks like vertical, but it's not vertical because you average over some regions like this, and if you take the convex rule of all these regions, you have a cone. Okay, so it's really a non-tangential maximal approach. Okay, and this is the definition of this guy. So you have this property also. This property is not as difficult to show as this one, but you really need this one to show this. Maybe, yeah, maybe I will. I had planned to give elements of proofs, but maybe just one indication. So you need a square function estimate. And resolvents and off-diagonal decay for the resolvents. So let me just mention what it is, off-diagonal decay. So for example, look at TT, which is 1 plus I T dB inverse, or the version with BD works the same, and T is a real number, or maybe positive. Well, could be a real number. And then the off-diagonal estimates are the fact that when you sandwich TT by multiplication by indicator functions of closed or Borel sets, E and F, then it's, of course, still an operator bounded on L2. But you want a bound that depends on the distance between the sets E and F. So E is some set here, and F some set there, usually some balls or something like this. Then this is a distance. Well, actually, okay. And then you want some decay in the distance divided by T. Okay, and then you want to measure the decay in a polynomial way, for example, with some order n. So for resolvents of any for any n. Okay. So you have this kind of estimates you can prove just by using the differential structure of this operator D here and commutator estimate. You can even prove exponential decay if you want, but polynomial decay to any order is sufficient. So you use this and that, and how do you make the connection? When you take your semigroup function, okay, and then you, let me put a T here just to the fun, and then what you can do is take away the resolvent at time T, like this, and add this up. Okay, so for this guy, in other words, you have replaced the semigroup, the action of the semigroup, by the action of the resolvent, but the resolvent has some decay, and you can use that together with some Poincaré inequalities at some point to prove that you have the upper bound when you replace here the L2 upper bound when you replace the semigroup by the resolvent. Now for this one, well, it's a function that's bounded holomorphic. It has obviously some decay at infinity, but it also has some decay at 0 because what? Because whatever the sign of z here, or the real part of z, this function at z equals 0 is 1. So it's 1 here, 1 there, so it's 0 at 0, so it's a psi function. Okay? And for a psi function, you can bound the non-tangential maximal function. You see this is an average over some cone. So this is less than an average over some cone like this in the sense of area functional. And then you can use this kind of estimates with not with this one, but with the psi. Okay, so let me not go into the details here, but you can really prove things like this here. Ah, yes. Okay, another corollary of this method is, for example, the fact that, let me come back to the solutions here. It could be true for this, but for the f, which is here, now if you decide to take averages of this f there, the one which you constructed for solutions. Okay, so it's, of course, the value of f pointwise doesn't mean anything. We only have L2 log, so we average on these Whitney regions. And now we can let t go to 0 and take a limit. but by fixing x. And if we do that for almost every x, we can prove that, in fact, this f converges to the initial value at time t equals 0, so that was this h. Okay, so you recover some kind of Fatou-type boundary value for those solutions, the solutions constructed by semigroups. So that's a good news. Okay, and then the last point is, okay, so I created a solution with a plus spectral space, so what happens if I start from an H over there, which is in the negative spectral space? Okay, if I take H in H2 minus, and I take the same formula for F, then, in fact, I create a solution of the Cauchy-Riemann equation, but not in the upper half space, in the lower half space. Okay, so the plus spectral space is for the lower half space, and the negative spectral space is for the lower half space. That's how it works. Okay, so that's, again, the splitting of function into holomorphic function above and holomorphic function below. The same kind of thing happening here. Okay. So in other words, what we have done is we have constructed a solution in this topology, which is the L2 topology, and we have a number of properties that are the properties that we like when we deal with boundary value problems. Okay, the sup L2 norms, the square function norm, and the non-tangential maximal estimate, and on top of that, we have almost every convergence. Okay, so now what we want to do is we want to change topologies. Okay, so what about other topologies? Okay, so let me just mention one for now, and then tomorrow there will be more. So some sub-F topology, for example. Okay, so let me just restrict to a range of exponents, sub-F exponent between -1 and 0. And then I look at the sub-F space, homogeneous space, which is just closure of test function of f over Rn as 0, which means that the integral of the function f should be 0. This is for this 0. For the usual semi-norm for the Laplacian, so I guess it's s over 2 applied to f in L2. Okay? Well, ultimately, it's a dual of h minus s if you want. And the fact that s is negative means that you can realize hs embedded into the Cn here, into the space of distribution. Okay, it's not. You can do that. You don't have any. You don't have to mod to the polynomial. So then you create a subspace of a closed subspace of it, which is the space of elements in this space, such that they are annihilated by the curl applied to the tangential part. Again. Okay, and then, so this creates a family of spaces, and then you have the following. So you pick f in h infinity of s mu. You don't want to be f to be defined 0 here. You only going to work in the range if you want. And then this defines f of dB. Now is an operator on the range of D. Okay, and the range of D, well, contains a dense subspace of hs of D, of course. Okay, so you may think of extended, okay, which is the same. Well, maybe if I do this for s equals 0, then this is the same thing of this. Okay, so now we have the following properties. F of dB extends to an operator on all this scale, hsd, with bound less than f infinity. Okay, so you have this. So this means that you can work with the spectral projections again, and they will be bounded on this space, and they define a splitting. Okay. Like this. And also you have the extension of the semigroup by this rule to this space. And you can characterize the norm in this space. So if H is in HSD, you can compute its norm, its HS norm, squared, via a square function of the following type. dt on t. Okay. So again, this is some kind of classical thing for sectorial operators, that you can characterize negative sub-Lf spaces by square function involving the semigroup itself, not the psi function, but the semigroup. Okay, so it works in this context and in this range of S. So to finish for today, two important values of S. S equal -1/2. So if f is equal to -1/2, the integral here, these powers of t cancel. Okay, and if I rewrite the integral in this form, okay, that's a function of x, so squared dt dx. And this is an integral of Rn plus 1 plus. So that's what I get. This is an L2 integral on the upper half space, which is just an energy integral. Energy class. Why? Remember that this was a solution of CR. CR, if H is in, so if H is in HS plus dB, then this is a solution of CR. So the semigroup is of the form of the conormal gradient of some solution for the PDE. Okay, now the conormal gradient, I didn't say it, but the length of the conormal gradient is equivalent to the length of the gradient, because you obtain one from the other by multiplication by bounded invertible matrices. Okay, so if you have an L2 estimate on the conormal gradient, you have an L2 estimate on the gradient. So this is the L2 integral of the gradient. So this is the energy class for this PDE. Okay, and the other case, which is very important also. Okay, and this class is very important, of course, because the energy class, because of the Gaussian inequality, you can use the Lax-Milgram theorem to prove existence and uniqueness modulo constant of solutions to the Dirichlet problem or to the Neumann problem in this class. So in this class, you always have existence and uniqueness of solutions. It's not a question. It's easy functional calculus. Okay, so you can use this class of solutions to prove estimates on in other topologies. That's the use of this kind of class. Another class which is important when you want to solve, for example, the Dirichlet problem. And I will finish with this. S equal. So S equals 0, we have seen it, so let me put that aside, but S equals -1. Okay? Then what do you get? So you take H again in H -1 plus dB. So again, your semigroup is going to be, in some appropriate sense, a conormal gradient of a solution U. Okay? And the square function norm that is over there, we write as T grad U Tx squared dt on dx. Okay, is equivalent to H measured in the topology of H minus 1. Okay? And so this is a classical square function norm in the L2 sense, okay, for the PDE. So notice that, okay, so a square function for solutions of divergence A grad U equals 0. Okay, and notice that on the right you have an equivalence with some quantity, and this quantity is what? It's a norm in the H-1 topology. Okay, but what is H? H should be thought as what? The conormal gradient of U at the boundary. Okay, so which is what? Which is the conormal derivative of U at t equals 0 and the tangential gradient of U at time t equals 0. So if you want to solve the Dirichlet problem for U, with U at time t equals 0 being in L2, its tangential gradient is H-1. So this is a natural topology for this object. And similarly, if U is in L2, then its conormal derivative should be thought as an element in H-1. Okay, so this is a natural space for setting up the Dirichlet problem here. Okay, so this is a space for Dirichlet problem with L2 data for div A grad. Okay, so let me summarize. For S equals 0, this is a space for example, for the Neumann problem with L2 data. For S equal -1/2, this is the energy class. And then you take the data, U at time t equals 0 to be in H1/2, for the conormal derivative to be in H-1/2, depending. And then for S equal -1, this is a space for the Dirichlet problem with L2 data. So you can embed all your boundary value problem into a scale of different problems, all for the semigroup in different spaces. And tomorrow I will keep going with looking at how these spaces, so changing the 2 into some P and telling you what happens in this case. So I'll stop here.
Kato's conjecture in this context, you said this.
The equivalent. Okay, the equivalent. Yes. Yeah, at least one direction. Let me just tell you. When I say equivalent, it's okay. I'm cheating a little bit. But you take the same D, and you take B now to be, so, and the Kato for, let me write Kato for divergence D grad in X. Okay, I want to study Kato for this guy in Rn. Okay, and then I take the B that comes from the A that was 1, 0, 0, D. And if I compute what the B is for this case, I get 1, 0, 0, D. And I take this dB, it's 0 divergence of X times D minus gradient of X, 0. And now the H infinity calculus for this dB, oops, sorry, it's unfortunate, but it will be recorded, I guess. Too late. Okay. The infinity calculus for this dB, for this one, is equivalent to having a square root of, let me write E, this operator, just square root of E applied to F in L2, equivalent to grad XF. Okay, so in a particular case of this B, okay, the H infinity calculus for this dB is equivalent to the square root estimate for this E over there. So when I said equivalent, I said, of course, in fact, you embed the square root problem here into a larger class of problems But for this larger class of problems, having B of this form or B of a general form doesn't change the nature of the proof. It's the same difficulty. It's just algebra is the difference.